So I'm going to start with a very quick summary of why we care about writing code. And I possibly should have added to this instead of just asking ChatGPT to do it for me as another justification. But if you write code that works, that will save you time compared to code that doesn't work. It will get you your data and your analysis finished so that you can actually do science with it. And it will let you explore whatever science questions you actually want to explore. And I could talk a lot more about various techniques you can use to save time and to do more science, but we're going to hold those for if there's enough interest, I can run another session, or if people want to chase things up later. I'm just going to focus on the basics of how you can use Xarray to save you time and to do stuff that you wouldn't be able to do without it. And I'm also going to say that ChatGPT is still terrible at Xarray and this kind of complex large data analysis because there's just not enough training data there. So it really is something that it's worth knowing a little bit about yourself and knowing where to start to ask the next questions. See what you can do. So I would say that writing code for climate science is not about answering complicated questions in the same way that just about any other coding task I've ever encountered is. So you're not trying to find, if I have all of these different shades of blue, what's the best way to paint this wall according to some aesthetic criteria? You're often trying to ask really simple questions. And for me, that's often, what is the average temperature in this box? But then you're trying to do that over and over and over and over again, or you're trying to do that in 50 bajillion different ways. And so the problem is not working out how to answer the question, but working out how to answer the question repeatedly across the huge data sets that we're working with. And so just as a simple example, if you have some climate model output, that's probably, let's say the atmosphere sits on a grid. So you're going to have some X direction, some Y direction, Z direction. So that's 3D. Mostly our brains can handle 3D as the space that we work with, but it's more complicated to wrap your head around the data on this grid than, say, an Excel spreadsheet where you've just got 2D data and everything's labeled like in front of you. And then unfortunately, you've also got a time axis. So you have one of these 3D grids every single time step of your model output or of your reanalysis. And so that gets kind of tricky to wrap your head around. And it's really annoying to try and keep track of what different axes are. And so the biggest thing that Xarray does for climate science coding is labeling those different dimensions. So instead of having direction 1, 2, 3, 4, you can say, well, this thing is longitude and this thing is latitude and this thing is height or pressure or whatever. And it takes that strain off you as a human into something that the computer's keeping track of. So over the course of next 12 minutes, 15 minutes from now, I'm going to hopefully explain what the Xarray library is, where, how, why you might use it, and then what that does to make your code work faster, to spread the load across different bits of the computer so it runs properly. And then given that we have this Xarray tool that can do stuff, how do you turn your science question into something that Xarray can do for you? So I'm just going to start by flicking to Gardy. Is that visible to everyone still? Yep. So I've imported a bunch of libraries, NumPy, Xarray, Matplotlib just for visualization. And I had time in here because I were doing some optimization last time I ran this, but it's not actually used for anything I'm running at the moment. And then I'm just going to arbitrarily generate some numbers. So this is the NumPy array. It's 12 numbers, one after another. It's got no metadata explaining what those numbers are, but we can plot them. We can go, huh, cool, it's a sine wave. But let's suppose that these are all measurements from 1 month of a year. It might be useful to keep track of that. So maybe we want to say that these numbers are numbers through time. So an Xarray array is a NumPy array plus some labels. So here we have this NumPy array set of numbers, that's the baseline. We also have a thing that's telling us that it's got one dimension, that dimension is time, and time has a length of 12. We've also got coordinates. Our time coordinates go 1 through to 12, but there's no limit on what these actually are. So if for some reason you've taken 4 measurements at different times, then you waited a year and you took another 4, your time coordinates could go 1, 2, 3, 4, 16, 17, 18, 19. So what Xarray does is it lets you attach that kind of metadata to your data and move it around together instead of having these numbers that you have to remember what each of them means. Making sense? Yep, cool. And the one other concept I'm going to introduce in the notebook before I switch back to the slides here is the idea of a task array, which we're not going to go into in much detail, but you can think of it as a NumPy array that's waiting to happen. It's not in existence yet. The computer is just keeping track of what it will be when it comes into existence later. So in this case, we have another Xarray array, but instead of coming up with a bunch of numbers, it's saying, yep, we have dimensions, time equals 12. It's going to take up this much space. It's going to be broken into pieces that are this big. It's going to eventually have a shape of 12, which is going to be broken into a bunch of pieces that are size 3. And these are all the things I'm going to have to do later to get it. So it's about the computer keeping track of what it's going to do later, but not doing it yet, which can be useful for basically sorting its life out and then going and doing it later once it's already sorted it out. But if we just switch back to some examples, this is 9 numbers. You may notice that they have numbers 1 through 9 because I'm not going into complicated examples today. And if I said to you, look, can you add up all these numbers for me? There's probably 2 ways you'd do it. You'd sit there with a calculator going 1 plus 5 plus 3 plus 7 plus 8 plus 2. Or if you had it on a piece of paper in front of you, you might add up these 3 and say, well, that's 8. This next lot adds 17, the last lot adds 19. And then you don't have to do it in your head. Or even I could go, cool, right, I'm going to add up the first 3. Joel, you're going to add up the second 3. Mahara, you can add up the third 3. And then we'll pull those numbers together at the end. Because there's no reason for this summing to be done in a particular order. And if those 2 are going to sit there while I'm doing maths in my head, they may as well do some work. And the same thing applies on Guardi, that if you've got an ARE session that's got, say, 14 cores, 28 cores, there's no point one of them doing all the work if actually everyone could help and you could spread that load out across the different cores. And it's also really useful to break these into smaller pieces because then you don't run into memory problems. Because just like I can't keep 9 numbers in my head at once, I need them written down on a piece of paper in front of me. The computer can't keep, I think your limit's going to be more than 20, 40, 100 gigabytes kind of numbers. So they're obviously much more than I can keep in my head, but there is still an upper limit. And so you still don't want to ask the computer to handle more numbers than it can fit into memory at once. And it turns out that basically anything you want to do can be done in this chunkwise approach where you split things into different pieces and then you do them bit by bit. So if you want to find a maximum, you could find the maximum for each of the 3 boxes and then merge it together later. Yeah. So if we switch back to Guardi again for a moment, we can spin up a thing called a Dask client. I am not going into detail, just copy paste this into the top of your code. It'll work. If it doesn't work, complain to me or Sam Green or someone else, a research software engineering team. There are various ways to optimize this, but generally you just want something that exists and that'll let you do maths on these little pieces one at a time. And then I'm just going to click Launch Dashboard for the purposes of showing what's going on. At the moment, I have 4 workers. This is because this ARE session is a fairly kind of it's a medium-sized one. It's only got 4 cores. I would thoroughly recommend that if you are stopping and waiting for your code, you put more cores in there because people time is so much more valuable than computer time. So if we take this array we had earlier, 12 numbers waiting to happen, we could take the average, sorry, that's the array, that's not the Dask one, that's the Xarray array. I can say I want to take an average through time. Because it's labeled as time, we can say dot mean time instead of saying dot mean axis 0 and having to remember what's what. I lost at least a day because I confused latitude and longitude before I found Xarray sometime in the middle of undergrad. It's really useful having labels on things instead of keeping track of what order they're in. We can take the Dask array and we can say I want to take an average of time. But because it's a NumPy array waiting to happen, not a NumPy array that's already happened, it's just going to say, yeah, cool, I could do that. If I did, it would be 8 bytes. It wouldn't have any shape. It would be a single number. And when I do it, it's going to be 1 chunk at the end, but we're going to have to do 3 things to it first. And if we use this thingy to visualize it, which I wouldn't recommend unless it's a really small sum, because otherwise the picture gets really complicated. What Dask is thinking it will do in the future is take all those different pieces, take the average of each of them, then we're going to have a bunch of pieces, they're going to come together again and spit out something. So it's exactly the same as what I'm showing here, that we're going to do some stuff with different pieces and then bring them together again at the end. And then if we want to take that average, so we have an average thing waiting to happen, then we stick .load on the end and run that. Then over here, it's going to go, oh, you want me to actually do some maths? Fine. And it's going to do some maths for us. If we do that with a bigger data set, so let's say this is error 5 SST from 2000, and I'm opening it with an Xarray open thing. Again, I would recommend just copy pasting this code with whatever data files you want to open at the start. And then these keyword arguments tend to make it run much faster and will work fine for climate data. This will make it run faster if you have any kind of task array set up. Now we have a sea surface temperature thing, and we've said, okay, 12 months, 721 latitudes, 1,440 longitudes. So you can have, at first glance, just see what size this 3D box is, 3D pile of data. It's got some sizes, and it's broken up into things that are size 1 in time and everything else in longitude and latitude. And then if we want to take an average, we can say, I want to take the average of this through time. And again, that'll then tell you, right, we have latitude and longitude coming out of that. There's going to be no time left because we're averaging through time and it hasn't done anything yet. It's waiting for you to tell it to actually do the maths. And then we can do that. And then it's done a bunch of individual pieces, merged stuff together and spat out a pile of numbers for us. Any questions yet? Cool. So the last bit of this quick summary is going to be about how you do something that is not just take a sum, take a maximum, take an average, but what if you actually want to do some kind of science? And when I first started doing this kind of stuff, I just copied and pasted code, and I was really confused about why I had to write these things in this weird way, because for loops tend to cause problems in Xarray because you're taking away its capacity to do things cleverly and do things one at a time and combine them. So you need to somehow have a single line of code that uses the Xarray words. And that's different to anything I'd been taught to do programming previously. And it's kind of like you're going along and you hit a cliff and you go, how the hell do I get up that? And what I'm hoping we can get from the next few slides is a bunch of stairs to work out how to get over that hump of, this is my complicated analysis that I want to do. How do I do it? And so I'm just going to summarize what's going through my mind when I'm approaching this kind of problem. And basically, when you have an Xarray array, you can do any maths to it. You can square root it, add some stuff together, logs, cumulative sums. Anything that is a maths thing you can do to a number, you can also do to an Xarray array. Anything that's a NumPy function, you can do to something in Xarray. You can take cosine, raise an exponential of something, other, whatever. You can also reduce the dimension in some direction. So if we have a 3D array and you say that I want to add up everything from the ground to the sky, that would be an addition through that vertical dimension. Or you might want to take the standard deviation through time. So that is getting your n-dimensional array one dimension fewer by reducing it in some way. You could also take, say, the maximum within any of these dimensions. So maybe you want to know at what latitude is the hottest temperatures. You could take a maximum through latitude and that would get you out data that's one dimension less. And generally, every time you make stuff at a lower dimension, you make it easier for your brain to understand. Other ones that exist here, argmin is the number in the array that the smallest is, or cell is I'm going to pick out one particular one. So you could cell at, I don't know, 200 meters height. Or if you were really interested in something around Canberra, you could cell at longitude is 135 and latitude is -35. Are those real numbers? It's accurate to plus or minus 5 degrees. I don't know precisely. So again, you're taking your big complicated data set and reducing it down to something that your brain is going to be able to understand more easily. There's some other weird stuff you can do that's occasionally useful. So shift moves the whole thing sideways, which I use if I'm comparing initialization and lead times of forecasts. So if I want to know what happened 3 years after something or other, I take one array, I take the other one, I shift it 3 years, and then I can compare them. Coarsen is lump things together into piles of a certain size. So I often use that for if you have super high resolution data, you don't want super high resolution data, you could coarsen in the longitude and latitude direction and average after coarsening. And then you would have a thing that's got the same number of dimensions, but less. It's shorter in each of those dimensions. And then where and group by are increasingly weird things. Where it picks out everything where a certain condition is true. So I want atmospheric temperature where it's land. Or I want to know my ocean temperature where it's rained. So you can find a way of seeing if something's true and then grab from another a data array given the first thing is true. Or group by is mostly useful for climatologies, where you can say group by the month of time and then average that, and then you have a thing that's different for each month of the year. The full list of them is here. The full description of what all of these things I've just said, apart from the NumPy ones, is here. So you can look into those in more detail. But that's kind of the limits of what you can do in any individual step. And then the question is, given some scientific problem, how can I break it down into these pieces so that I can do something useful? And if all else fails, it is possible to throw something into a pile, pretend it's an Xarray function and pass it through. I'm only sharing this so that you know it exists. Should you encounter it in future, you can go, oh, Jemma said that thing once that might work for this thing. And you can try and chase it down. I use this for sci-fi functions when I don't want to write my own. But let's just pretend it's not a thing for my own. How am I going for time? Can I do all 4 examples or just keep 2?
I think we're fine for time.
All right. We're going to go through 4 examples then of things that you might want to do in code, how I can explain them in words, and how we can turn those words into code that can actually be written. And I'm going to start with the Nino 3-4 index as the idea I introduced at the start, where I have a box of sea surface temperature that I want to average. So we can say that. I want to calculate average sea surface temperature within this region for every time. And I can break that into 2 ideas. You want to get the sea surface temperature within the Nino 3-4 region, and you want to average it for every time. So to get it within the region, if you're sitting on a regular grid, you could use .cell, which is selecting stuff. So you could select with latitudes within this range and longitudes within this range. Or if it was a weird grid, you might want to use .where, and you could use SSTs where the latitude is less than -5. That's backwards. That should be a greater than. Latitude is greater than -5, and latitude is less than positive 5. And longitude is more than 190, and longitude is less than 240. So when all of those conditions are true, when you're this side of this wall and this side of this wall, and like down from this wall and up from this wall, that'll get you inside the box. And then you can average it with this .mean function. And if we're off the equator, you might need to apply some kind of weighting as well, because things get pointy towards the poles. But near the equator, you can effectively assume that each of the points will equally contribute to that box. Second example would be if you wanted to take a rolling weighted average. I had someone ask me about this, I think last year, possibly the year before, which when you put it as that simple line can seem kind of complicated, but you could also break that down into, well, a rolling average is a rolling sum of my weights times my data divided by the rolling sum of my weights. And now we're in terms that you can break all of those individual pieces into something that Xarray can do. So we'll start with this whole weights times data thing. That's a math sum. We can do that. Let's multiply the weights by the data. Then we can break that into rolling pieces by saying I want to have a rolling window of that. And let's say we're breaking it into time steps of size 3. And then we're going to take the sum of that rolling window. And so now we have the top half of that equation, which I've just called numerator here. And then the bottom half you can do in a very similar way. You take the weights you make that some kind of rolling thing, and you add up all of the stuff within each of those rolling boxes. And you can divide those just with A divided by B. That's the denominator. Someone needs to rewrite these slides.
I do have a quick question.
Yep.
Which of these are Xarray functions, or are they all just NumPy?
All of these ones are Xarray, apart from this, which is built in Python.
Cool.
NumPy would be if I had np dot something or other. I guess it's possible that that's back-ending onto something in NumPy to make it run fast, but that wouldn't be something you need to know. This is one that really threw me when I first started coding like this, which is trying to find the depth of the 20-degree isotherm. And again, we have all these shorthands when we speak in like spoken English or written English for what a concept means. That makes it hard to really break it down into the simplest possible pieces that you need to explain to the computer. But we can say, okay, we want to find the 20-degree isotherm. That means we need to find the depth that is 20 degrees. You can actually break that out again and say, fine, we need to find the deepest depth that's warmer than 20 degrees. That's going to be the point when we move across the boundary. And you can interpolate from that afterwards, but I'm just going to start on that one and say, right, we can break that into two pieces. Let's find all of the water that's warmer than 20 degrees. So that's our warm depth. Let's say where our data set or our temperature is going to be bigger than 20. And so that's going to end up with all of this blue bit, let's say that's colder than 20 degrees, if that's our cutoff. And then we can use argmax to find the deepest depth that's still warm, if we're going to say this is the warmer one. Or IDX max will give you the depth index coming out of it. And then you have a number that's how far down you have to go to transition across that temperature boundary. And you can do extra interpolation stuff if you wanted to.
With that example,
yep.
Sorry, just with that previous example, your two questions. When you say at step 1, depth dot where ds is greater than 20, is depth and ds the same data set?
ds would be temperature, and depth would probably be ds dot depth if we're being.
Oh, yeah, okay.
So this would be a coordinate on the data set.
Yeah.
This one would be the actual temperature of the data set.
Okay, okay. And the second question is, you're like, just to understand, you're wanting to get you want to get a one-dimensional array of depths. Is that right? So you'll end up just with like a one-dimensional array.
In this picture, you'd end up going from 2D to one-dimensional. In practice, I actually needed to go from a 3D ocean to a 2D ocean, like looking down at the surface, what's the height. But yeah, in that picture,
but this is just in one, I guess, latitude slice. Okay. Yeah.
Yeah.
Yeah. So do you specify the depth? Oh, sorry, hang on. I'm taking up a meeting room. I'll switch my camera off in a sec and move out, but I just want to check that the depth is like, do you need to specify that you're working along the longitude you mentioned? I'll turn off my camera, but I'm still listening.
No, you need to specify that you're collapsing along the depth dimension. So this bit here where you take argmax through depth, you need to specify that you're reducing along depth, but whatever's going to be left in this particular case being latitude or longitude, however we're reading this picture, is going to still be there at the end. It's just that. So if we started with 3D ocean, depth, latitude, longitude, you would take the maximum along depth and you'd be left with latitude and longitude. Or here, if you start with, let's just say this is lat, and then you collapse along depth here, you're going to be left with just latitude at the end. Are we going to assume that makes sense to Greta? Cool. Thanks. Last example, I think, is the most complicated thing I've tried to do with Xarray, and it still can be broken down to like 3 or 4 steps. Nice. Which is just trying to make a forecast by finding months in a large pile of model output that look similar to some particular target month that we've started with. Which again, when you phrase it in English, loses a whole bunch of the like individual steps along the way, and it gets tricky to chase through. But really, you just need to find the most similar ones, or find how similar they are, and then find the most of those similars. So I started by calculating mean squared error. So SST minus the target SST, so this is just maths. Square it, also just maths, and take the average. And then you have a single number for any of these months of how similar they are to your target that you're starting with. And then you can just sort them, or you can find the index which has the lowest error, so that's the most similar, or you can sort them and grab the first few off the end. But so even this really complicated concept of we want to find months that look like this other thing, try and make them match up, can be broken down into just, okay, how similar are they? Now we have a single number, which is the smallest of those numbers. That's my answer. And with that, I'm going to wrap up my initial summary. If you want to learn more about any of these things, I can recommend talking to the RSEs. I'm happy to be asked questions about this kind of stuff. So I'm a bit overwhelmed at the moment. I'm not likely to reply to you very quickly. Sam Green has a setup thing for making Dask work and a few other resources out there. Or there's a YouTube recording of a talk I gave that's kind of the next step on from this talk to a customer access NRI audience sometime through last year. And Slido there.
First question, is the best practice to split out data into the same number of chunks as the cores available?
If you want to know more about chunks, go watch this thing. But in general, I would say you want at least as many chunks as there are cores available. If you have fewer than that, there's going to be cores sitting there doing nothing. And you want your chunks to be taking around a second if you can get the sums to be around a second, because otherwise you've got too much overhead from the scheduler trying to do stuff. And if they take too long, it's a nuisance. And you want your chunks to easily fit into memory. So if you're having any kind of memory issues, so if this blue bar over here, if anything starts to go orange, then you need smaller chunks.
You would cry at my code.
That's good to know. Did not know that the colors meant something.
Yeah, blue is I'm happy. Orange is I've hit a point where I think I have too much stuff in memory and I'm a bit sad about it. The little gray bar after that means your code is slowing down lots because the thing's going, too much memory, and it's writing stuff down, which takes about as much extra time for the computer as if you sat there and wrote down the numbers that were in your mind to come back to them later.
Good to know.
What's the difference between .compute and .persist with Dask? The next.
Something or other about whether they end up hanging around on the individual workers or in some kind of more centralized memory. There is a difference. I always use .compute. .load is the same thing as .compute, except it puts it back into the same box again. So if you screwed up, it's less likely to force you to have to reload the whole thing later. Persist theoretically works, and I know people who are good with code who use it, but I don't know the details because I don't use it. I think it's supposed to leave things in memory on the Dask stream instead of trying to centralize it all back together again. I think it's useful with stuff that you might need to use on repeat, but it's not your final output.
I was looking into compute and persist yesterday, and that aligns with what I learned. So that's great. Another question was, does Xarray store all the data in memory if you're not using Dask?
If you are not using Dask and you do anything with something you've opened that is not just open it and verify that it exists, then it pulls it all into memory. I guess, or if you sub-select it, there's some. So if you open it, you take a sub-selection and you do some maths with that, it'll only load into memory that sub-selection to do the maths with. So it can do some really crude approach to just grabbing some bits out of the files, but it doesn't do the same lazy computing thing of holding stuff that it'll do it later and it'll just get the bits that you need.
Do you recommend always using Dask?
I would recommend using, if it fits into memory, load it into memory. NumPy does a bunch of this distributing stuff out to be done together as well.
Are the bytes printed for an Xarray dataset the bytes required for data plus computations, or just for data?
Just for data. A good rule of thumb is to double it. That's been my experience about when things start to crash out, is that actually it wants twice as much as it says it needs. If you're doing anything funky or complicated, like let's say you had a data set through latitude and longitude and another one through latitude and time, and you're going to somehow merge them, so you're going to end up with a 3D data set, then it's going to need way more memory, but generally just double the number of bytes it says it wants. Do it.
Cool. Okay. I think this is the last question in the Slido. How do you recommend dealing with multiple files, like with Error 5, where the climate variables are stored across multiple files?
If you're doing initial data crunching to make stuff small, you could handle them individually. Normally what I would do is I would use this openmf dataset, which is a multi-file dataset command. And then you can give it a thing called a glob string, which is this asterisk will pick up anything in that gap. So it'll take anything in this folder with whatever happens to be there. And in this particular case, that's 12 different months .nc. And then you can do weird things where you hand it a whole list of files and say, I want you to merge these in this way. So I would generally recommend opening with OpenMF dataset, unless it's really not working or it's huge and you just need to get that first thing down to something more manageable, in which case handle them one by one, maybe even stick it in a for loop. If the stuff inside your for loop is taking 30 seconds to 5 minutes to run, then your for loop isn't adding much overhead. And then you can save things as smaller pieces and do stuff with that later.
Cool. That's good to know.
I've got a question, just since you've got this here. So when you do that MF dataset,
Yep.
you've got parallel equals true,
Yep.
and it's a chunk dataset. So is parallel equals true is just going to like auto chunk it, and then parallel equals false, just a normal Xarray?
Either of them will chunk it. The
Okay.
thing that'll make it be chunked is the fact that it exists in multiple files. The error 5 is weird because each file seems to be only one chunk. Mostly stuff has multiple chunks in a file. And what parallel equals true is it says, yes, all of the workers can help open this file. I have no idea why it's not true by default.
Okay.
Otherwise, you end up waiting for ages while one of the cores goes and gets the file for you.
Okay.
Yeah, and thanks for everyone for joining online. We're not sure what the next month is exactly going to be, but look out for it. Thanks for coming, everyone.